At this point, we have learned how to form a kernel map from a truth table, and we're ready to start using a kernel map in order to create a minimized sum of products logic expression. Kmaps can also be used to create minimized product of sums logic expressions, but we'll start with the sum of products form. Okay, so let's take our two input example, and we'll put it next to us so that we have that. And then we'll list the rules out and apply it to the two input. So we had two input variables, A and B, 0 and 1, 0 and 1, and this was cell 0, this was cell 1, this was cell 2, and this was cell 3. And we had the inputs 0, 1, 0, 1. So this is the same information that's in a truth table. What we want to start doing now is using a process to identify variables which can be removed from a canonical sum of products logic expression. And ultimately what we're trying to do is form product terms that can produce more than one output row that's asserted. Okay, so what we want to try to do is create a product term which can handle or cover multiple rows that have their outputs asserted. Okay, so the rules of this are as follows. The first thing you want to do, and this is a very graphical process, so we want to circle groups of ones. Okay, so we're actually going to go into the Kmap and we're going to circle groups of ones. But there's some rules that go along with this circling. So the first thing we want, or the first caveat with this circling groups of ones, is that each circle should contain the largest number of ones. Okay, so that's just saying make the circles as big as possible. And these circles only cover neighboring cells. So for example, if you had something like this, where you had a 1 and a 1, you don't circle diagonally. Okay, so you never circle diagonally, you only do neighbors. The next rule is that the number of ones circled should be, not even should, it must be a power of 2. And that means if you had, for example, if you had like a 3-input Kmap, and let's say you had 1, 1, 1, and you went to circle, you would circle this, not all 3 of them. Okay, so it had to be a power of 2. So that's going to be circles of 1, 2, 4, 8, and 16. And we stop there because we never really go above a 4-input Kmap. Okay, and then another rule of this is circles don't encompass other circles. Okay, so they don't encompass other circles. And what I mean by that is that if you had a circle like this where you circle a 1 and you had something like that, you wouldn't circle like that. So you cover all the ones with a circle. You would not have the need to have both of the ones circled individually. So as soon as a 1 is covered with a circle, it's taken care of. And you enter as many circles as necessary in order to cover all the ones in the Kmap. Okay? And then finally, each circle is called a prime implicant. And what that means is that we're going to take a prime implicant and we are going to create a product term which will produce the ones that it covers. Okay, so we can actually, there's a set of rules in order to create that. Okay, so let's apply this. There's multiple rules here. We're not to the end yet, but let's go ahead and do that. Let's do this on this Kmap. So what I would do here is I would be able to circle this one right here, but since it has a neighbor, I can go ahead and pick that up. So the example applying this logic to here, notice that I would circle those two. Every one is covered in this Kmap, and I didn't put circles around the individual ones because that would have encompassed it. It's a power of 2. There's 2 cells covered, and that would be the circle. Okay. Now you could have other circles. If this would have been a 1, you could have added a circle there. And it's okay to have circles cover each other like this. Like let's say you had 1, 1, 1, 1, it would be, or 1, 1, and 0. It's okay to do a circle like this. So that's fine. You can cover something multiple times. But for this example, that's what the circle would be. Okay. So now step 2 of this is creating a product term. So we're going to create a product term for each prime implicant. And this also has some rules associated with it too. Okay, so I'll draw a line there. So what we're going to do is evaluate each variable one by one, and then you're going to do the following. If the circle covers a region where the variable is a 1, leave in the product term uncomplemented. So uncomplemented. If the variable is a 0 for the region that the circle covers, you leave in the product term complemented. And this will look very similar to when we were creating the sum of products in the canonical form. We've really not done anything until we get to this step right here, where if the variable is both a 1 and 0, exclude it. So we finally have gotten to a situation where we can exclude the variable from the product term. Okay, so we got that. And what we're going to do is we're going to create a product term for each prime implicant. The final thing that we do is then we sum all product terms. And that gets us finally to the sum of products. So let's apply this to the 2-input Kmap. And you get used to this by doing example after example. So let's take a look at this. What I want to do is I have one prime implicant. That means I'm going to have one product term, and that will be it. I'm not going to sum multiple product terms together. I have one circle, which is one prime implicant, and that's one product term. So let's evaluate this variable by variable. And this is where it's handy to have the variables listed outside. So this is where you have A naught, this is where you have A, this is where you have B, this is where you have B naught. And so let's go through this product term, or this circle, variable by variable. There's two variables. So let's start with A. This circle covers a region where A is both a 0 and a 1. So what I mean by that is that the circle covers these two columns. So it covers this region where A is both a 0 and a 1. You can see that that corresponds to the region where A is both A and A naught. So what I can immediately do is I can exclude A from the product term. So I've gotten rid of A. A has no impact on the circuit. And then what I do is I come over and I look at variable B, and the circle covers a region where B is a 1. So I include B uncomplemented. So I do it uncomplemented. So the product term for this is simply B. Now I sum all the product terms together. Since I only had one, all I do is I just say F is equal to B, and that is actually the minimized logic expression. Now if you think about that, let's look at the truth table for this and see if it makes sense. So I have A, B, and F, 0, 0, 0, 1, 1, 0, 1, 1, and I had 0, 1, 0, 1. If you look at this, it is indeed F is equal to B. So look at when B is a 0, F is a 0. When B is a 1, F is a 1. When B is a 0, F is a 0. When B is a 1, F is a 1. A had no impact on the output. So we can create the exact same logic functionality from this truth table by just saying F is equal to B. Notice that if we would have created a canonical sum of products form, we would have had something like this. F is equal to A naught ANDed with B, ORed with, that would be for that row, and then ORed with A ANDed with B. And you would have said, well, that's interesting because it took a lot of logic expressions, but I could have recognized from the distributive property that I could have pulled B out, and I would have been left with A naught ORed with A, and I would have noticed from the complements theorem that that would have been, I can replace A naught ORed with A with a 1, and then from identity, anything ANDed with a 1 is a B. So I could have done this algebraically, but I was able to accomplish it graphically using this algorithm. So this algorithm is very nice because we can apply it to larger and larger circuits, whereas the algebraic model kind of breaks down because when you do it by hand, you have to identify these visually. So you have to look at it and just hope that it comes to you what you're going to do, and that's not a good way to do anything. What you want to do is come up with a very methodical algorithm that you can then automate using a computer tool and apply it to more circuits and larger circuits. Okay, so now that we know how to do it, let's do two more examples. Let's go back to a 3-input Kmap, and let's see how we can do this, and we'll just walk through the variables one by one. So let's take our 3-input Kmap, where we had 8 cells, of course, and the inputs were A and B and C. We had 0, 0, 0, 1, 1, 1, 1, 0, and they had 0 and 1. And these cells were 0, 1, 2, and 3, and 4, 4 and 5, you gotta be careful, and then 6 and 7. And let's just say we had these outputs, so 1, 0, 1, 0, 0, 0, 1, 1. So that's the Kmap as we start. And what I want to do here is let's go ahead and jot down the variables as they would be entered into the product terms in a sum of products. So I'm going to have A and A naught, and then I'm going to have over here I've got C naught and I've got B. Down here I'm going to have not C naught and C. Down here I'm going to have B, and over here I have B naught, and here I have B naught. Okay, so let's apply our rules. First thing we want to do is circle ones in powers of 2 and make them as big as possible. So I'm just going to start up in the upper left corner, and I'm going to try to circle this guy. So it has no neighbors going to the left, which would have been over here. It does have one to the right. In fact, I see a neighbor over here. So I go and I'm going to pick up this one. The question is then, do I pick up that one? And the answer is no, because that would be 3 ones in the circle. That's not a power 2. So I end my circle there. And then I'm sorry, this should be a 1. I'll make it just a little bit easier. I want to show you a 4-input Kmap, or a 4-input circle. So now I have this right here, and I'm going to start trying to pick up these ones. So what I can do is I come along and I'm going to circle this one. It's got a neighbor here, but look, it's got neighbors up here also, and I'm going to pick up all 4 of those cells. So this illustrated something important, and that's why I wanted a 1 right here. So this is a 1. I wanted to show that you can overlap 1s as long as these circles aren't within each other. So notice that this cell right here, this cell number 2, is covered by 2 circles. But it's okay because the circles did not fully encompass each other. Okay, so this is valid. So now in this situation, we are going to have 2 prime input. We're going to have 2 prime implicants, which result in 2 product terms, and we need to figure out what the product term is by going through the Kmap input variable one by one. So let's start with this circle right here. So we're going to cover this. We're going to talk about the circle that covers 0 and 2, and let's go one by one through the input variables. A. This circle covers a region where A is a 0. So I bring it in as A naught. Okay, so I bring it in complemented. Circle covers a region where B is both a 0 and a 1, or notice that it covers B and B naught, so I exclude it. So I have a situation now where I can exclude B from this product term. And then finally, it covers a region where C is a 0, which I bring it in complemented, or C naught. So I'm going to have A naught and it was C naught. So the product term for that circle that covers 0 and 2 is A naught and it was C naught. Okay? This product term, for all the input codes that are put onto it, it will assert for input row 0 and input row 2. Okay. Notice now we move along, so we're going to move along to the next product term, and I'm going to go through this 4-cell circle, input variable one by one. So let's start with A. It covers a region where A is a 0 and a 1, so expand this boundary, A is excluded. It covers a region where B is a 1, so I bring it in uncomplemented. And then finally, it covers a region where C is both a 0 and a 1, so it spans this region here, so I can exclude C. So the product term for that circle is simply B. The final step in this is coming along and summing all my product terms, and I now have a minimized logic expression for this Kmap. It's f is equal to a naught n with c naught ORed with b. Okay, so let's do one more example kind of to solidify this approach, and let's do our a 4 input example. So let's just say we had a 4 input Kmap that had 16 cells, and it's going to have input variables a, b, and c, and d. So I'm going to go a, b, c, d. So the inputs are 0, 0, 0, 1, 1, 1, 1, 0, and 0, 0, 0, 1, 1, 1, 1, 0. And let's just pop the outputs in there. So we're going to go 0, 0, 0, 0. These are just the outputs for this example. So then 1, 1, 1, 0, and then 0, 0, 0, 0, and then 1, 1, 1, 0. So I come along and I'm ready to start circling. It's useful to put the variables along the outside, so let's do that really quickly. So let's call this is going to be the columns corresponding to a is equal to 1. In an SOP, that's going to be a. And these are the columns corresponding to when a is a 0, so it's a naught. And then these columns right here are going to be where b is a 1, so I put it as b uncomplemented. And then these columns right here are where b is a 0, so I label them as b naught. These columns right here are where d is a 1, so I'm going to label that d. These are going to be where d is a 0, so I'll label them d naught. And then finally we come over here and we have c is a 1 right there, and c is a 0 right there. Okay, so we have the Kmap, everything's labeled, and it's time to start circling. So this one is interesting because it illustrates how neighbors can wrap around. But let's start with identifying circles. Okay, so step 1 is I'm gonna pick up this one right here. Notice I can put a circle here, and I was able to get 4 ones in it. Okay, so that's power 2. Now I go to get these ones. Well, one of the things I can notice is this is a neighbor, but indeed these two are neighbors also. Since a neighbor can actually wrap around, what I can do is I can make a 4-cell prime implicant by wrapping around. So I kind of draw this thing like this to indicate it, and I actually have 2 prime implicants in this. Okay, so let's now begin by creating the product terms for each prime implicant. And let's start with these cells right here. So we're going to start with these 4 cells, and then we'll do the second prime implicant. Okay. All right. So this is going to come over here, and I'm going to go through one by one through the input variables. So A. This circle covers a region where A is both a 0 and a 1, so I exclude it. This circle covers a region where B is a 1, so I bring it in uncomplemented. This circle covers a region where C is a 0, so I bring it in complemented. This circle covers a region where D is both a 0 and a 1, so I exclude it. So the prime implicant, the product term for this is C naught, don't forget the naught, is going to be B AND with C naught. The next thing we do is let's do the circle corresponding to these 2 bottom ones, and this I'll fill them in just to kind of differentiate it from the other circle that I did. So now I'm doing those 4 right there. So what I'm going to do is go through one by one on the input variables. So this circle covers a region where A is both a 0 and a 1, so it spans this boundary. A is excluded. This circle covers a region where B is a 1, so I bring it in uncomplimented. Now we got to pay attention here. This circle, because it wraps around, so it's not as easy to see. This circle covers a region where C is what? Well, it covers this region right here. So it's got C and C. So it's actually where C is both a 0 and a 1. So it's actually C is a 1 and a 0. So C is excluded from that product term. Then we come back and we look at this circle covers a region where D is both a 0. So it's a 0 and a 0. You can see it right here from our labels that the region is where it's D naught. So I bring that into the product term, complement it. So the product term for that prime implicant is going to be B AND with D naught. Okay, so from here we can simply finish this by ORing all the product terms together. and you now have the expression. Now notice something that's interesting about this. This is a very minimal logic expression, because if I would have done a canonical sum of products, I would have had 1, 2, 3, 4, 5, 6 product terms, each having 4 inputs, and then I would have had a 1, 2, 3, 4, 5, 6 input OR gate. I have now a sum of products, which is simply 2 AND gates feeding into an OR gate that look like this, where I have B and C naught, and then I have B and D naught. Now, the Kmap doesn't do that final associative property if you wanted to pull B out. So I noticed B's in both of those, so I could have said B is ANDed with C naught, ORed with D naught. The Kmap doesn't take it to that point. Okay, the Kmap just gets it into a nice sum of products form, so you would have to do that manually if you wanted to. Okay, so this expression right here would give you where B was ANDed with, you'd have C naught, or like C naught, D naught, or together, and then you'd have this ANDed together. Okay, so you would pull B out of there. So the Kmap doesn't give you this. A lot of times this doesn't buy you much though, because you're already at you already have 3 stages of logic. So you have your inverter, AND gate, OR gate. So you still had inverter, AND gate, or OR gate, AND gate. So you still have 3 levels of logic. But I just wanted to highlight that. So that's the procedure that you use to take a Kmap, basically take a truth table, go into a Kmap, and then take the Kmap and create what we call a minimized, this is important, minimized sum of products logic expression.